let's recap capacitors in parallel again. So we did KCL on this node. So that current is going to be the sum of all those currents. And we know that current through a capacitor, let me put I sub C so it's not equal to the current source. This equation is not equal to the current source, current I. That's C dV dt. So each one of these terms we can substitute that. I1 is through capacitor C1, so we put C1 there, dV dt. I2 is through capacitor C2, so we have C2 dV dt, and it's the same voltage across all these capacitors because they are in parallel. All the way up until the nth capacitor. And this is just going to be a summation of all the capacitor values from k equals 1 to n. Multiplied by the time differential of the voltage across the capacitors. That's equal to I. So this summation term is going to be the equivalent capacitance if we wanted to combine all of these n capacitors in parallel into one capacitance that functions equivalently to all those capacitors in parallel. Okay, so when we are when we have capacitors in parallel, the equivalent capacitance is going to be the summation of the capacitors in parallel. This also makes intuitive sense if we think about the capacitor equation. Okay, so the equation for capacitance was the permittivity of the material between the two plates of the capacitor times the area of the capacitor plates divided by the distance between the capacitor plates. Okay, so let's say all of these capacitors are the exact same. So they have the same size, same material between the plates. And I'm putting them all in parallel. What am I doing to this capacitor equation? Am I changing permittivity? I'm changing area, yeah. I'm not changing permittivity because they're all the same capacitor, all the same material between the plates. Permittivity is a material property. I'm not changing the distance between the plates because they're all the same capacitor. But by combining all of these capacitors in parallel, I am changing the area, right? If I have 10 capacitors in parallel, that combination is going to have 10 times the area of a single capacitor. So it makes sense that as we put capacitors in parallel, the capacitance value should increase. And that tracks with our equation here because we're summing up the capacitance values. The only confusing thing about this is that if you had resistors in parallel, right, you're not summing them up. You're doing a summation of the reciprocals and taking the reciprocal of that. So when you put resistors in parallel, the equivalent resistance goes down. Okay, for series capacitors, this is going to be like resistors in parallel. So let's do, to see why, or to see what the equation is, let's do KVL around that loop. So what's my KVL equation? Start at this point and go around the loop. I heard all the right terms. I'm not sure. I couldn't hear the signs, so I'm not sure if the signs are right. So V, they're all added. What's the sign of V?
Oh, sorry, minus V.
Okay, so minus V plus V1 plus V2 plus V3 dot 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 all the way to Vn is 0. We also know that the voltage across a capacitor is 1 over C from time t naught to t of the integral of the current through the capacitor plus the initial voltage across the capacitor at time equals t naught. Yeah, that was the equation that we had from last time. So if we, let's make our KVL equation V equals V1 plus V2 dot 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 to Vn. And that means that V will be equal to 1 over C1 times this integral and the initial voltage V1 plus 1 over C2 times the same integral, because all of these are in series. So the current through these capacitors is all going to have the same value. I could have a different voltage across capacitor C2 at time equals t0. And so forth. Okay, so this integral term here is going to be the same for all the capacitors. So I can say it's going to be 1 over C1 plus 1 over C2 dot 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 to 1 over the nth capacitance value multiply by that integral and I also need to sum up all of the initial values. The initial value of V1, initial value of V2, up to the initial value of Vn. If I want to know that voltage V. This part here, within the parentheses, is going to tell me 1 over CEQ. Because now if I wanted to find the voltage across this capacitor CEQ, in the right-hand simplified schematic, my equation for that would be V equals 1 over CEQ multiplied by the integral plus the initial voltage across that. Okay, so this term in the parentheses is telling us that the reciprocal of the equivalent capacitance when they're in series is going to be the sum of the reciprocals of all the capacitors in series. So that's the same form of equation as resistors in parallel, but the capacitors are in series. I'm running out of room on this slide, so I'm going to rewrite this on the next one. So for capacitors in series, this is the formula for finding the equivalent capacitance of n capacitors in series. So when I'm putting capacitors in series, the capacitance, the total capacitance, or the equivalent capacitance, is going to decrease. Similar to resistors in parallel. Okay, so let's use these methods of simplifying capacitors in an example problem. So given this circuit, or a network of capacitors, find the equivalent capacitance. And I'm going to put this on class question. I forgot to log in, so give me a second, but you can start solving it now. Okay, our class size is roughly half the size of what it usually is. So I think most of the responses are in. Okay, good. Most of you got it correct. Let's run through this really quickly. So this is going to be just like simplifying a resistor network, except we have to use different equations when they're in series and parallel compared to resistors. Okay, so I'm going to combine two steps into one redrawn schematic. So I'm going to first combine the 50 and 70 microfarad capacitor into an equivalent capacitance. I'll leave the 20 microfarad capacitor alone for now. And then I'm also going to combine the 60 and 120 microfarad capacitor in series to another capacitance, CEQ2. Everyone okay so far, right? This is just like, so far this is just like resistors. Now here's where it's going to get different, because CEQ1 is the parallel combination of capacitors, but I just need to add them up. So the mathematical operation that I'm doing is different from parallel resistors. So CEQ1 is 120 microfarads. CEQ2, those are in series, but the form of the equation is like parallel resistors. So it's 60 microfarads multiplied by 120 microfarads and divided by the sum. And this is going to equal 40 microfarads, which is also the final answer, but it's just coincidence that it's the same. Everyone okay with these steps so far? Any questions on this? Okay. Then let's simplify some more. Leave CEQ1 alone for now. And then let's combine the 20 microfarad in parallel with CEQ2. So let's call this CEQ3. So this is going to be, they're in parallel, so I'm just going to sum the two capacitance values. 20 microfarads plus 40 microfarads. So this is 60 microfarads. And CEQ1 was 120 microfarads. And then finally, we just want one capacitance between the two terminals to get our final answer. And we can get that if we combine CEQ1 and CEQ3 in series. So this is going to be 120 microfarads times 60 microfarads over that sum of the two. This equation is also the same as this equation. So our final answer is 40 microfarads. Any questions on this example? Okay, now let's do a little bit trickier example. Here's a similar circuit, multiple capacitors. They're connected to a 90 volt DC source. And now I want to know if I have this arrangement of capacitors, what's going to be the voltage across each capacitor? Okay, so the first question is, how are we going to relate, or what's the equation that we're going to use for voltage across a capacitor? What equation do we want to use? Okay, let me just give this to you. So we're going to use the equation for charge on a capacitor. So the charge on the capacitor is the capacitance times the voltage. So if we can figure out the charge on each capacitor, we know the capacitance values. We can figure out the voltage across those capacitors. Now the question becomes, okay, how do we figure out the charge across these capacitors? Well, if instead of this circuit, I gave you this circuit, you would be able to tell me the charge on that capacitor. Because you know the voltage on that capacitor. What's the voltage on this capacitor? 90 volts. If we knew this value, then we would know this C. So we would know C is some value, voltage is 90 volts, and we would know the charge on this capacitor. So we need to get from our circuit on the left to the circuit on the right, and then we can figure out the charge on the capacitors in this circuit. Okay, so how do we go from the circuit on the left to the circuit on the right? Okay, so step one, let's combine the circled capacitors in series. So my schematic then becomes like this. Let's call this EE211. I'm combining them in series. So it's 60 microfarads times 30 microfarads divided by that sum. Which is 20 microfarads. Okay, then step two. combine CEQ1 and 20 microfarad capacitor. Combine those in parallel. So this is going to be CEQ2. What's the value of that going to be? 40 microfarads. So it's 20 microfarads plus 20 microfarads. So 40 microfarads. Okay, so we have two 40 microfarad capacitors in series. So we can combine those again. I'm going to draw that on the next slide because I ran out of room. Okay, so step 3. Will result in this circuit because I'm combining the two series capacitors from the previous circuit, and this is what I wanted. And this is (40 microfarads in series with 40 microfarads. So just like two parallel resistors with the same value, I just get half the capacitance, or 20 microfarads. Okay, and we were going to use the equation for charge. On a capacitor. So the charge on that equivalent capacitance will be 20 microfarads times 90 volts. Or about 2 millicoulombs of charge. This is the charge on that equivalent capacitance. Okay, so I know how much charge is being stored in the combination of all the capacitors. But the question was, what's the voltage across each capacitor? So I know these four capacitors together are storing 2 millicoulombs of charge. I just need to know how that charge is distributed across all those capacitors. So let's go back a step. So and look at the schematic for step 2. So let me draw it on the side over here. So step 2, our circuit schematic look like this, where we had CEQ2 here and 40 microfarads here, and CEQ2 is also 40 microfarads. Okay. Current is related to charge because current is the change of charge with respect to time. So what can we say in this kind of circuit where my elements are in series? What can we say about current through those elements? it should be the same. Okay, now since current is related to charge, for capacitors in series, the charge on those capacitors should also be the same. Okay, so because of that, I know that the charge on those two capacitors will have the same value. So let's and I also know that the charge across the 40 microfarad capacitor was V1 according to the original schematic. So I have enough information to write sorry, let me start from the original form of the equation. I have enough information to figure out V1. Okay, so the charge on that 40 microfarad capacitor is going to be 40 microfarads times V1. And what's that charge going to be? .0018 coulombs divided by 40 microfarads will give me 45 volts. In that same schematic, V2 is still going to be, V2 is the voltage across that 20 microfarad capacitor, but CEQ2 is this 20 microfarad capacitor in parallel with the combination of the 60 and 30 microfarad capacitor. So the voltage across that combination, because they're in parallel, is still going to be V2. And if I have 45 volts across capacitor V1, what's V2 going to be? 45 volts. So V2 is 45 volts. Or we could plug all the numbers back into this Q equals CV equation, but you have the same numbers, so it'll give you the same value. Okay, so we have a value for V1 and V2. I'm out of space again, so I'm going to go to the next slide. And now let's look at the schematic that we had from step 1. Or actually, just look at the original schematic, sorry. Oops. No, I was correct. The first time, not the second time. Okay, so the schematic from step 1 look like this. This is CEQ1. Okay, we solved for V2, which was 45 volts. What's the voltage across CEQ1?
45 volts.
It's in parallel to the 20 microfarad capacitor, so the voltage across CEQ1 will also be 45 volts. Okay, so let's figure out the charge on CEQ1. So we know the voltage across it is 45 volts. The value of CEQ1 was 20 microfarads. So this is going to be one more zero. No, too many zeros. This is going to be the charge on CEQ1. Now, what is CEQ1? So CEQ1 represents the 60 microfarad capacitor and the 30 microfarad capacitor. Those are in series. So they should have the same charge across them. And so we know what the charge is going to be. So to find V3, it is the charge divided by the capacitance. That's 15 volts. To find V4, that's the same charge divided by a different capacitance. That gives 30 volts. Okay, so V1 V1 was 45 volts, V2 was 45 volts, V3 we just found is 15 volts, V4 that we just found is 30 volts. So we are we can check to make sure that we didn't make any mistakes here by checking the circuit in another way, which would be KVL. So if we do KVL around this first loop, what's our equation? Let's call that loop 1. Starting at the base of the arrow here, going around that loop. 90 volts equals V1 plus V2. And if we put those values in, so 90 volts equals 45 volts plus 45 volts. And that's correct. Okay, that's true. We satisfy KVL for that loop. Let's do KVL around loop 2. 45 volts equals 15 volts plus 30 volts. Okay, that's another true equation. We can also do KVL around the outer loop if we want. That's loop 3. What's that KVL?
90 equals 45 plus 15 equals 30.
Okay, 90 volts, voltage rise equals 45 volt voltage drop plus 15 volt voltage drop plus a 30 volt voltage drop. Okay, that's also true. So we can double check what we did here by making sure we're also satisfying KVL. How about KCL? How come we didn't check this with KCL? We could do KCL at this node here. What's KCL? Let's call this I1, I2. Sorry, this is getting pretty messy. Maybe I can use a different color. I1, I2, I3. What's KCL at that node?
You're right.
Okay, I1 is equal to I2 plus I3. That's correct, but what are the values for I1, I2, and I3? 0, because I have a DC voltage, so my voltage is not changing as a function of time. That means the current through the capacitors should be 0. So this is 0. It still works. But even if I solve the voltage values wrong, I'm going to get this for the KCL equation. Any questions on this example? Okay. Then, since we know about capacitors, let's think about something else. So resistors dissipate power. In our water analogy, they're like the pipes that the current or the water flows through. Capacitors store and release energy. They're like the water tanks that can store and release the water. Inductors are an element that can store energy as well, but I start to lose the effectiveness of the water analogy because we're storing energy in a magnetic field, and the water is supposed to represent charge. I don't have another representation for the magnetic field. But in the mechanical version of the system, where resistors are dampers, capacitors are springs, inductors are going to be like the masses in a spring damper system. Another point, so inductors will store energy in the magnetic field. Like a capacitor, it can store and release energy. And in any electrical circuit, you are going to have some inductance there because you will have wires in your electrical circuit. When you have current running through those wires, that is producing a magnetic field. So in this class, we are, we said whatever wires we have in our schematic, there's no voltage dropped across them. We can make them as long or as short as we want. That's not actually true in a real circuit, because you will have some finite amount of resistance in a wire, and as you make the wire longer, you're going to increase its inductance. So if you're not accounting for inductance in the circuit, and you make a circuit with a really long wire, that might have a non-negligible inductance and affect how your circuit behaves. But again, for the purposes of this class, wires are just wires. Don't have to treat them like inductors. If we have inductors, we are going to draw them specifically in the schematic. These are just some pictures of real inductors. So here's an example of a coil of wire around the core. This is a different shape of the core. It's a toroidal core. And then you can also have inductors that look like the resistors that you're using in the lab. They're used a lot in things like power supplies. And they're also used in filter circuits and oscillator circuits. So, for example, the circuits in your mobile phone that are used for the communications part of it, those have a lot of inductors in them. Which actually is a problem, because inductors take up a relatively large amount of space in a circuit. Okay, so here's that coil inductor. It's just a spiral of wire around the core, and that's why the circuit symbols for an inductor just look like a coil of wire. For inductors, we can define some important parameters. Is class over? Which would be the length of that wire coil, the area circled by that coil, the number of turns in the coil, and the material in the cross section. And all of those parameters will give you a value of that inductor. But we'll talk about that in the next class.